In this video, we're going to continue our discussion on resonance structures. So there's a few rules that we need to follow when we're drawing resonance structures. Number one, we don't break sigma bonds, also known as single bonds. Number two, we don't exceed an octet of electrons on any of our atoms. So for instance, carbon wouldn't have 10 electrons. It would only want 8 electrons. Number three, we only move lone pairs of electrons or pi electrons. And remember, the pi electrons are the double bond electrons. And then number four, we use arrows to quote unquote push electrons. Now, in actuality, the electrons aren't moving, they're actually delocalized. But when we're drawing the resonance structures, we're a little limited with the Lewis structure rules. So we can't really show that they're delocalized until we draw our hybrid structure. So down below we have an example of how to push electrons. So in the brackets we have our resonance structures. And you'll notice that on the left-hand side we have a central carbon, and it has a double bond to one oxygen and then a single bond to the other oxygen. And the oxygen on the right has a negative charge. Now, remember that molecules want to be stable. So if an atom can share its negative charge or even its positive charge with another atom, it will. So in this case, we can move electrons around in order to stabilize the molecule. Or another way of thinking of it is the electrons can delocalize in order to stabilize the molecule. So what we can do is we can move a lone pair of electrons from that negatively charged oxygen down to make a double bond. But when we do that, we're violating the octet rule for carbon. If we make a double bond there, carbon would have 10 electrons. So in order to make sure carbon only has 8 shared electrons, we're going to move this pi bond up onto oxygen. So now we've created a pi bond or a double bond between the central carbon and the oxygen on the right. And when we did that, that oxygen lost its negative charge. Then we also moved pi electrons up onto the oxygen on the top, and that made it a negatively charged oxygen. And you can calculate the formal charge for each oxygen just to verify that those are the correct formal charges. But now that negative charge is shared between two oxygens, and that makes the molecule more stable. So then we can draw our hybrid structure and show that the electrons are actually delocalized between those two oxygens, and they're each sharing the negative charge, so they actually only have half of a negative charge. And this is more stable. Okay, so let's go over a couple more examples of resonance structures. So essentially what we're doing here, and this is going to sound a little silly, but it's a good example. We're taking, we're taking a blue horse. Oh, horse. Oh, that could have been bad. and a red donkey, and we're making a purple mule. So we're taking two different structures, two different Lewis structures, and we're combining them to make a mixture. And we're creating our hybrid. Okay, so let's look at the two examples we saw in the last video. We had our allele cation, which had a double bond and a single bond. And then one of the carbons was positively charged, so it was missing an electron. Now, we also saw that the three carbons were sharing that or I guess two of the carbons were sharing that positive charge. So what we can do is show that the pi electrons, so the double bond electrons, are actually moving. Well, they're not really moving, but we'll say they're moving for now. And that's going to give us our second resonance structure. And I'm using the bond line drawings for these molecules, but if you want to draw in all of the hydrogens too, you can. Okay, so again, the pi electrons are moving over, quote unquote, to give us a positive charge on the carbon on the left instead of the carbon on the right. So now let's draw the hybrid structure. So we're going to draw our three electrons, and remember each of those vertices or termini is a carbon. And the double bond is actually delocalized across those two bonds there. So each carbon has a partial positive charge. Okay, so now let's look at the allele anion. So this looks similar to the allele cation, except we have a lone pair of electrons on the carbon on the right, so that is negatively charged. So how can we move electrons around to give us the resonance structure? So what if we move these pi electrons over like we did with the cation? So that would give us something that looks like this. But remember that carbon on the right also has two hydrogens bonded to it. So let's say that big dot is our carbon. Does that make sense? No, that carbon has too many electrons. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. But additionally, remember this carbon on the left has only 3 bonds now because we moved its double bond over. So it will be positively charged. So that's just a mess. Carbons would prefer to be neutral. So having both a positive and a negative carbon in the same molecule is not great. It's not very stable. Okay, so we can't move, oops, I erased too much. So we can't move the lone pair of electrons over, so we have to do something else in order to share that charge with another carbon and make it more stable. Okay, so what if we move this lone pair down and create a double bond? Okay, so then we would have Two double bonds, right? And the carbon in the middle, remember, does have a hydrogen bonded to it. So does that make sense? No. So that carbon now has 5 bonds, and carbon would prefer to have 4. This is actually what's known as a Texas carbon, which has 5 bonds, because everything's bigger in Texas, right? But this violates the octet rule because that carbon has 10 shared electrons. So carbon cannot have 5 bonds. That's really important. This is one of the biggest mistakes we see in organic chemistry. Students will give a carbon 5 bonds because they just forget, it's easy to forget that carbon can only have 4 bonds. So always double check that your carbons do not have 5 bonds. Okay, so that doesn't quite work. What we'll probably have to do is also move these pi electrons over. So when we do that, that should give us our second resonance structure. Oops, already drew it wrong. There we go. So now the lone pair of electrons is on the carbon on the left. And now that negative charge is shared between the carbon on the right and the carbon on the left. Okay, so typically when you move a lone pair of electrons down to make a double bond, you need to have a double bond next to it so you can move electrons further down the line. And it depends on the molecule, but the allele anion here is a pretty typical example of how electrons move. Okay, so let's draw the hybrid structure. So we can see that between those 3 carbons, the electrons are delocalized, but this time we have a partial negative charge on the 2 carbons on either end. Okay. So for both of these molecules, we have delocalized pi electrons. And that makes the molecule more stable. All right, let's look at another example. Oh, wait, I forgot. If you want more practice with hybrid structures, I recommend going over the Skill Builder 2.6 exercise on page 66. All right, let's go over our next example. I'm going to draw a molecule. Let's see, so we've got a carbon bonded to 3 oxygens, and one of its bonds is a double bond. All right, so let's figure out the formal charges on each of these oxygens. So what is the formal charge for this first oxygen on the left? -1. So if you see an oxygen with 3 lone pairs of electrons, it's going to be negatively charged. What about the oxygen on the right? That is also negatively charged. And then what about the oxygen up here? That does not have a formal charge, so we'll just leave it as it is. Okay, so now how can we move electrons around so that those two negative charges are shared? How can we stabilize this molecule? Well, let's try moving a lone pair over. If we do that, are we violating any of our resonance rules? Yes. So if we only move that lone pair, carbon will have 5 bonds. And again, that's a Texas carbon, so that doesn't work. So if we do move those lone pair or that lone pair down, we have to also move the pi bonds from our double bond over as well. Okay, so that will give us our second resonance structure. Okay, so the oxygen on the right still has a negative charge. What about the oxygen on the top? What is its formal charge? -1. It has 3 lone pairs now. And what about the oxygen on the left? It does not have a formal charge because now it has a double bond to carbon. Okay, so is there any other way that we could move electrons around? What about the oxygen on the right? We haven't done anything with that yet. So let's move one of its lone pairs over. Okay, but again, when we do that, we're creating a Texas carbon. So now we need to move these pi electrons over as well, so that we don't violate any octet rules. Okay, so now we have a double bond on the right. So now what is the formal charge of the oxygen on the left? Negative. And the oxygen on the right? It does not have a formal charge. Okay, now looking at these 3 structures, these are our resonance structures, so we'll put brackets around them to show that this isn't a reaction that's occurring, we're just showing a movement of electrons. But additionally, are these 3 structures the same or different? So they're technically different in the sense that the double bond has moved around. But if you think about their energy, do they all have the same energy? Yes, because really we're just rotating the molecule in a sense, right? So all 3 structures have the same energy. So we would call these, oops, whoa. Yeah, my iPad wants to really zoom in on my molecules here. So they all have the same energy. So that means they are degenerate. So degenerate's just our fancy word for same energy. But again, these are our resonance structures. Okay, so now let's draw the hybrid structure. So I want you to pause the video and try to draw the hybrid structure on your own first. And then when you unpause, we'll go over it together. Okay, so let's draw our hybrid structure. So I'm just going to draw a single bond between carbon and each oxygen. And we just saw that the double bond is, or the pi electrons are shared among each of these three bonds. So we can draw that dashed line along each of the three bonds. So really, those two negative charges that we saw before, those are split up or shared among the three oxygens. So each oxygen has a partial negative charge. And I'm just going to draw the lone pairs here. And then a partial negative. Okay, so if that charge is divided up, or if those two charges are divided up among three oxygens, that means each oxygen has negative 2/3 charge. Because we've got two charges divided between three oxygens. Okay, so if you want more practice with this as well, I recommend trying the Skill Builder 2.7 exercise on page 68. Okay, so let's figure out how to identify localized versus delocalized electrons. How do we know if electrons can move? And how do we know if electrons just stay put? So let's look at a different molecule. Let's see. So we've got a nitrogen bonded to a methyl group, CH3. It's also bonded to a second methyl group. And then we've got a carbon double bonded to another carbon. And that carbon has a CH3 group. Okay. And then nitrogen also has a lone pair of electrons. Okay, so let's see how we can move electrons around, potentially. So what can we do here? How can the electrons move around? So what if we move this pi bond over here? No, we can't do that, right? Because that would give this carbon 5 bonds. So that doesn't work. What about this lone pair on nitrogen? Can we move that over? No, because that would also give that carbon 5 bonds. So what if we move this lone pair over here between the nitrogen and the carbon in the middle? Does that work? Well, initially it looks like the carbon in the middle will have 5 bonds, but that carbon has a double bond next to it. So that means it has pi electrons that we can move over. Okay, so let's draw that structure. Let's see what it would look like. I'll draw it down below here, since this is a fairly large molecule. Okay, so now we would have a double bond between nitrogen and carbon. And then we'd have a single bond on the other side of that carbon. And then the carbon on the left there will have a lone pair of electrons. Okay, so, I mean, carbon normally doesn't want a negative charge. But remember, those electrons are actually shared between multiple atoms. So in this case, it's probably okay. So now let's think about formal charge. What is the formal charge on nitrogen in this particular structure? And if you want to pause and calculate the formal charge, you can. Okay, so the formal charge will be +1 on that nitrogen because remember, nitrogen has 5 valence electrons. In this particular structure, it doesn't have any lone pairs of electrons, and then it's sharing 8 electrons. So that's 5 minus 4, which is +1. Okay, now what about this carbon here? What is its formal charge? Well, I already showed you, right? It's negative. So we've got 4 valence electrons and then 2 lone pair electrons, and then carbon is sharing 6 electrons. So that's 4 minus 2, which is 2, minus half of 6 is -1. Okay, however, this is still a legitimate resonance structure because those electrons can delocalize. So what we end up with is, again, a hybrid structure. So I'm actually going to erase these and show you the hybrid structure. And remember, you can always rewind these videos if you need to see the original structures again. Okay, so let's look at the hybrid structure. So we've got nitrogen, and it has delocalized electrons with the carbon in the middle, which also has delocalized electrons with that other carbon there. And then we'll just draw the other groups that were unaffected by this movement. Oops. Let's see. Got a hydrogen. Okay. So the nitrogen, oh wait, I'm missing a hydrogen. So the nitrogen on the left there has a partial positive charge because remember, initially it didn't have a formal charge, but then when we moved to the electrons, it had a positive charge. So it really just has a partial positive charge. And then the carbon on the right has a partial negative charge for the same reasons. Now, one other thing, what is the hybridization of the nitrogen? So let's think about its steric number. How many things is it bonded to? 3. So if it's bonded to 3 other groups, is it sp hybridized, sp2 hybridized, or sp3 hybridized? sp2 hybridized. Now, if nitrogen was sp3 hybridized, its electrons wouldn't be able to move. So that nitrogen has a p orbital that's hanging out, and sometimes that lone pair of electrons is in that p orbital, sometimes it's not. It's kind of a mix, but without that extra p orbital that's hanging out on nitrogen, it wouldn't be able to delocalize its electrons. So the nitrogen must be sp2 in order for the, oops, I keep flipping the slide, I apologize. In order for the electrons to delocalize. And those are going to be in a p orbital. So this is really important because if something is sp3 hybridized, that means the electrons can't move. They're stuck in place. So we'll look at an example of that as well. So I'm going to redraw this structure, but we're going to draw it a little bit differently. Okay, so this time the central carbon does not have a double bond with the carbon on the right. So can we move this lone pair of electrons on nitrogen over? No, because we don't have any other electrons to move around. And if we move that lone pair over, the carbon in the middle will be a Texas carbon. So it will have 5 bonds. So we can't do that here. So there are no resonance structures because moving the lone pair results in a Texas carbon. Or another way of saying that is you're violating the octet rule. Okay, so if we can't move those electrons, what is the hybridization of nitrogen? Is it sp, sp2, or sp3? So let's start with the steric number. What is the steric number of that nitrogen? 4, because nitrogen's bonded to 3 things, and it has that lone pair of electrons all the time because it can't move, right? So if the steric number of nitrogen is 4, what is its hybridization? sp3. All right, so nitrogen is sp3 because the lone pair is localized, which means it cannot move. So again, this is a really good way to identify whether you have localized or delocalized electrons. Is an atom sp2 hybridized? Is it sp3 hybridized? If it's sp2 hybridized, that means the electrons are in a p orbital, so they could move. But additionally, you have to look for that combination of a lone pair of electrons and then a double bond nearby. Now, if you want more practice with this, I recommend trying the Skill Builder 2.10 exercise on page 82. Okay, so next time we're going to rank resonance structures because not all resonance structures are equal or degenerate in energy. And some resonance structures will contribute more than others to the overall hybrid structure of a molecule. So we will talk about that next time.